This is 6-4, Properties of Special Parallelograms. Our first definition that we need here is a rectangle. A rectangle is a quadrilateral with 4 right angles. Notice how we name rectangle ABCD on the right. There's no symbol in front of the letters, but we do name it with all 4 letters. So we have some theorems that go along with rectangles. Remember that the arrows are if-then statements. So our first theorem is saying that if we have a rectangle, then we have a parallelogram. So our rectangle fits all of the classifications of a parallelogram. For instance, the opposite sides are congruent, the consecutive angles are supplementary, opposite angles are supplementary, and our diagonals bisect each other. So if we have a rectangle, then it's a parallelogram. Tells us that we have a lot of qualities of parallelograms that we want to keep in mind. May help us solve for side lengths or angle measurements, etc. The next theorem states, if we have a rectangle, then the diagonals are congruent. So with a parallelogram, the diagonals weren't necessarily congruent, but they did bisect each other. Now, the diagonals will not only bisect each other since it's a parallelogram, that specifically for a rectangle, the diagonals will be congruent. So the length of BD, let me make that thinner, that's horrible. Try that again. Okay, the length of BD is congruent to the length of AC. And we can mark that. I'll just actually write it below. The length of BC is BD, sorry. Length of BD is congruent to the length of AC. I didn't want to mark it because then it might look like the diagonals are bisecting each other, which they are, but I want to stress more so for rectangles that the diagonals are congruent. So in this example, I'm noticing here that FG is equal to 24 inches. So this piece right here is 24 inches. FH is this diagonal, is 34 inches. So since a rectangle is a parallelogram, I know that the diagonals bisect each other and also the diagonals are congruent. So since FH is congruent to, let's change the color here, EG, and I know EG is also 34 inches, but I know that these parts are equal to each other. So if I'm looking for JG, let's change the color again, this yellow part, JG, would be half of 34 inches, so that would be 17. So knowing the theorems allows us to find the lengths of different sides or angles in a rectangle. Take a minute to try this problem, pause the video, and when you're ready for the answer, go ahead and play it again. So I want to clarify here, it's hard to tell, but I want you to realize that LJ is 30.8 inches, and GK is 48 inches. And since I knew this was a rectangle, I knew that the hypotenuse had to be longer than 48 inches, so that's how I knew that LJ really must be just half of the diagonal, 30.8. So without even seeing what I need to know here, I do know that HJ is 48 because it's a rectangle, it's a parallelogram, so opposite sides are congruent. I know that diagonals bisect each other since this is a parallelogram. So GL is also 30.8, or I can find the whole length. GJ will be 30.8 times 2, 61.6 for the whole diagonal. So let's see what, just from thinking about that now, I'm going to look and see. HJ is what they're looking for. HJ I already found, 48 inches. HK is the length of the diagonal. Well, remember I found the length of GJ, the diagonal was 61.6, so that's actually also the same as HK, since in a rectangle, diagonals are congruent. Another special parallelogram is a rhombus. Rhombus is a quadrilateral that has 4 congruent sides. And we label it as rhombus ABCD, so it doesn't have a symbol in front, but it does have 4 letters again. So if we have a rhombus, then we have a parallelogram. So a rhombus meets all qualities of a parallelogram. If we have a rhombus, diagonals are perpendicular, so the diagonals will definitely form a right angle. That's going to be important here. And if we have a rhombus, then each diagonal bisects the opposite angles. Let me pull up a picture of that so you can see. So notice angle B, for instance, was bisected. It created 2 congruent angles. We can't call it angle B anymore. It would be like angle ABD and angle CBD, for instance. Well, those 2 angles are congruent to each other because of the angle bisector, which in this case is the diagonal. So with the definition of a rhombus, we know that all 4 sides are congruent. So I can set these measurements equal to each other, 9x minus 11 equals 4x plus 7, and solve. Pause the video and try to solve that, and I'll place the answer here for you. So I solved for x. I got x is 3.6, and you can find each measure now. If you plug in that 3.6 into, for instance, for ST, plug it into 4x plus 7 to get 21.4. So for this example, I know that this angle is an angle bisector. So if I knew something about the other angle, I would be able to figure this out very easily. But I don't, so I'm going to skip that one for now, and I go to this angle right here. In a rhombus, the diagonals are perpendicular, so this forms a right angle. So I can say that 2i plus 10 equals 90, and I solve to get y equals 40, and I could plug that in and calculate the angle measurement over here. That'd be 42 degrees for an angle measurement. For these type of problems, we're going to have to show if the diagonals of a square are congruent perpendicular bisectors of each other. So you really want to break down those 3 words. Congruent perpendicular bisectors. So the first thing I'm going to see if the diagonals are congruent. So let me write this. Congruent. And then we get down here, I'm going to do perpendicular. And then below that, I'm going to put bisectors. This helps us break everything down so that we're looking at for the diagonals of the square. So we're talking about, let's look at what diagonals we've been talking about. BD and CA. We first want to show that they're congruent. The way that you find the length, and you should know this from the Chapter 7 project, the length of those lines would be to do the distance formula. So if you remember, it's x2 minus x1 squared plus y2 minus y1 squared. And then take the square root of all of that. So I calculated AC to be radical 58, which needs to be simplified. We got to check if that's simplified or not. But it doesn't matter too much in this case because we're just trying to show that they're congruent. And when I calculate BD, I also get radical 58 when I use the distance formula. So these 2 things prove that those diagonals are congruent. To see if they're perpendicular, they'd be negative reciprocal slopes of each other. So we can use rise over run and see if they're negative reciprocals. So to get from B to D, for instance, I would go down 1, 2, 3, 4, just kidding, down 3, over 1, 2, 3, 4, 5, 6, 7. So that'll be negative 3 over 7, down 3, over to the right, positive 7. And I'm going to do the same thing for AC. I'm going to count the rise and run. So 1, 2, 3, 4, 5, 6, 7 over 3. And so these are negative reciprocals of each other. So remember, when something's perpendicular, they want negative reciprocals, which is the flip of the fraction. So negative 3 over 7, you flip the sign first, it becomes positive, and then flip the 3 over 7 to 7 over 3. And now the bisector part. We want to see if these are we want to see if they have, not if they are, we want to see if they have the same midpoint. Bisect would give us the same midpoint. So remember, when you find midpoint, it's an ordered pair. It's x1 plus x2 all divided by 2. That's finding the average. Then we average out the y's. We add them, and we divide by 2. And we're going to do that twice. We're going to do it for BD, and then we're going to do it for AC, and we're going to see if we get the same midpoint. If we do, then these are bisectors. So here's our ordered pair. 1/2, 7 over 2 is what you get when you find the midpoint of both diagonals. Since they both have the same midpoint, I know that, and everything else, we have congruent side lengths, congruent diagonals, and we have perpendicular diagonals. And our midpoints are the same for the bisectors, so therefore, these diagonals are congruent perpendicular bisectors.